So I wanted to talk a bit about build and package management, which is something that we've spent a lot of time on in Mynewt. So this is kind of our standard marketing slide, and then I put up together a number of, or really two other slides that goes a little bit more in depth into the decisions. Oh yeah, sure. So hey, I'm Sterling. I'm CTO and co-founder of Runtime. Runtime is one of the contributors to the Apache Mynewt project. My background is from a company called, my background it started kind of self-taught, worked on the PHP programming language, worked on a lot of back-end and web server infrastructure, and then spent 10 years at a company called Silver Spring Networks that did deeply embedded work, over 23 million network-connected streetlights, power meters, distribution automation devices. Our first product, we ran IP stacks on 802.15.4 on 128K of code on an atmega. We dealt with battery-powered devices and moved all the way up from that to 7 TDMIs to Cortex M's and designing our own system on chips. We then founded a company, Pace and I just founded a company called Runtime, and the goal was to develop an operating system that made it easy for people to develop these connected products, because a lot of the issues we had at Silver Spring were we created our own operating system, and what we saw is most companies who do these deeply embedded connected products create their own operating system. So you have your own flash file system that you've developed in-house, or you have your own networking stack that you've developed in-house. And over time, you have to grow a platform team that becomes very specific to your company. So when you need to do something new, it's very expensive, right? We have this IP stack that we've put all of this effort into, and now we need to support IPv6, or we need to support 6LoWPAN, and we can't use a new IP stack because we did all of the testing on our old IP stack. And so challenges like that. And so the idea behind the Mynewt project was to create that open source operating system, very similar to Zephyr and mbed efforts. So one of the elements of that operating system that we spend a lot of time working on is the concept of build and package management. So kind of taking in spirit what we saw from Node.js or from Go. I think Go was a big influence on us. How do you go and compose an embedded project? And how do you make that reusable? And this is especially important in areas like an operating system where you have very, very constrained code, and you have a broad set of use cases for RTOSs, right? Some people want to use an RTOS on an Ethernet connected device and drive a display screen. Some people want to do a Bluetooth connected wearable. And so there's all this diversity. And so how do you help people compose the right system, allow them to reuse components, but still have something that makes sense and isn't crazy? So I think some of the goals we had there were to maintain reuse in packages across multiple products. So a big challenge that we had was we had meters and streetlights and distribution automation devices. 95% of the code was the same between those. But there were different and various configurations that we had, and we had our own build system that we built, which was just a bunch of make files that we had managed over time. So how do you, as a product company, you're probably going to have the same code base and 10 different products with slightly different requirements, and you should have a tool that makes things easy for you to do that. Manage, build, and debug in production setups. So, pretty much every embedded developer and every embedded project, you have to get your tool chain up and running, right? You have to go to OpenOCD, and it turns out that OpenOCD, has the wrong configuration for the board you have. Take ST boards as an example. ST-Link keeps getting upgraded and on these boards, and there are different OpenOCD configurations for each of those, most of which are out of date, right? If you use, there's 5 different debugging protocols from SWD to DAP-Link. So the person who's creating the board support package, in I guess our view, should also be the person who's creating the debugger scripts for that board support package and supporting the various debuggers that you do. So when you go and you download an operating system or you download a project, you should have the person who made the board support package actually support your debug setup, but also you should have a tool that allows you to go from debugging to production. Right? If your build system, the first part of your build system is making something and loading it onto a device, but then you want to take that same source code base and you actually want to create a downloadable image from it. and you probably want different build settings for that image. You probably want to use different security keys, but you need a single system that takes you between those two. And then, yeah, so in talking those, and I guess I'll leave it for questions, and I want to keep this somewhat interactive. So, the first kind of decision you have to make is whether you make the system composable or not, right? So, if you look at the build and package management tools that are out there, in some of them, you have just a file and you type install, and that installs all of the packages for you. But there's no enforcement of hierarchy in your directory tree, and there's no enforcement of things like a unified set of defines or where defines are put. And so it makes it very hard to compose a system that puts those together. So a lot of this is, how do you create a new project? How do you install dependencies for that project? And how do you make sure that all of the different elements of those dependencies follow a unified system? So in Newt, what we've done is we've enforced directory hierarchy on the various different projects. So I don't know, is that similar to what Zephyr does? Or does Zephyr not have a enforced hierarchy? It does, yeah. So, I mean, I can just jump to a terminal. Actually, that might actually be the easiest. What were you going to say?
Yeah, so I was saying, not necessarily. I mean, there is some structure, but this is like in the OS itself. But when you are an application writer, there is no strict hierarchy there, yeah, that you need to do. And right now we don't really have the support for external modules where we can say, where we have to say you have to build your module or your component in a certain way. But that's probably will be coming soon. Yeah.
So what we enforce here is the concept of a source directory and an include directory. The source directory gets recursively built. So everything in source that you can put whatever you want. Those devices will get built in there, except for one directory that we put in source, which is the ARC directory. So we have ARC x86, which is our simulated environment. We have ARC ARM, and then you can do ARC ARM Cortex M0. And so those directories are ignored in source, but everything else is recursively compiled in the source directory. And then in the include directory, what we do is essentially go and have include has OS as the first element in it. So the name of the package that's being built is always the first element in the include directory. GCC doesn't support include aliasing, so there's no way of saying, hey, I want to have the following package directory aliased there. So we have to enforce a hierarchy, which means that everybody who develops a package will prefix that with their package name. And the goal is to just avoid a mess of includes. You can see here that there's also the architecture specific directories here. So in include files that want to actually include something that's Cortex M0, essentially what we do is we have on that ARC directory, we go into the specific directory like Cortex M0 if you're compiling with that architecture, and then osarc.h is taken from that directory depending on which architecture you're compiling for. So if you want to have architecture-specific header files, you just put them in there aliased.
So this is basically your core directory structure?
Yes.
Okay, and I mean, are users expected to go and change that? Or, I mean, I'm not following exactly what structure are you trying to enforce here? Somebody writing, is that a component in this case? Exactly.
So everything in our build system is a package, and so we have the concept of projects and packages and repositories. So projects are a collection of packages And when you write, when you create a new project with newt, you type newt new, your project. At that point, you can then add packages to that project. In the case of the operating system, it's a package. And so all packages follow the same structure, which is they have a package.yaml file that defines the package and their dependencies. So in this case, you have dependencies listed for this package. So the operating system package requires the system initialization package, which defines system initialization order. It also requires libs-util, which has some memory management elements to it. Then, depending on whether or not a CLI has been provided or core dump support has been enabled, there are additional dependencies that are listed. Beyond that, you have include source and test directories in the package. So the build system has the concept of a unit test suite in it. So if you want to go and run a test on a package, all of your tests are located in that package directory, and when you write newt test, it will compile the tests and run the tests for that package.
And the idea here is that these packages are interchangeable, and you can actually put something else other than what Mynewt might actually provide?
Absolutely.
And how do you guarantee the interfaces are actually compatible? I mean, is that defined, for example, between an OS and the boot package? Is there an interface which is defined that guarantees that whatever I put there actually works?
Exactly, yeah. So what we do is the build system itself has a concept of APIs. And so within Mynewt itself, obviously, we have our own APIs for OS. We haven't agreed with other projects on, what we call OS mutex acquire or OS mutex release. But we do have the concept in the build system of APIs where a package can say, I require the console API. And the console API is what I define as console. What will then happen is some other part of the build system can actually include the console package. So you might, for example, in the board support package, decide whether you want a console for the specific hardware platform you're using, or you just want to stub it out because you're running simulated. What the OS does is it says, I require the console API. I don't care what package it has, just so long as that dependency is satisfied, and then it resolves that for you. So this is also similar when you want to do things like IP stacks, right? And you want to have you might want to have multiple IP stacks that you have. You don't really care which one is selected. You just care that it conforms to a very specific API you've done, and then all of the packages that are written expecting that API will automatically take the dependency once it's satisfied. I don't know if that...
Yeah, but I mean, why would you want to do that at this low level of things? Yeah, I mean, don't you want actually people to use one console or one IP stack and focus on that? I mean, the interchangeability is all fine.
Yep.
But then you are just basically giving too many options, and there are too many ways to do one single thing, and that basically drives users and developers crazy if actually, because it works here, doesn't work here, and this is better, this is, footprint is large here, footprint is small here. So why not focus on one single thing that actually works? And
I think it's things like console as an example. It is the one we use APIs probably the most for. And we have a console API that's stubbed out. You can either run a console on x86 or you can run a console on the specific hardware platform you're running on. Those are different packages and have different code footprint sizes to them. The various packages within the system don't want to specify whether you bring in the full console itself or whether you just have it stubbed out, but they want to kind of everywhere just write things to the console.
Also, it's basically different functionalities. For example, two different file systems that have completely different features that are supported by one single API. Yeah.
Exactly.
Okay.
And all that you care about is that there is a package that satisfies the file system API.
Can you go inside the source?
Oh, sure.
It's hard to hold it. Yeah. Okay. Yeah. So my understanding is you include
folder is mainly just contain those public head files, right? Just public ones.
Exactly.
But inside your source, you can still have private head files.
That's right.
Right. And inside source, do you have the hierarchy down inside the source folder, or is flat?
We just go and recursively compile source,
Okay.
except for ARC.
Right. Okay. So inside the source, it actually have more folders like for each component. Or
If you want to have them, yeah.
okay, I see. Yeah. Got it.
I don't know if we want to dive too deep on this, but how are APIs defined? Or is that from top down from the project? And how are they versioned, if at all?
So let's not go into versioning. We'll go into versioning. We use the same versioning system across APIs, dependencies, and everything, so let's save that one. But APIs, essentially, packages export the APIs they implement. So if the lib console or sysconsole full exports the console API, packages that then use console require the console API to be there. And so then that's automatically happened, and of course those APIs are then versioned.
But if you need a new API,
Yep.
and it hasn't existed before, is the system just flexible? Is it like
Yeah, you just export it.
Key value tag, you just export that, and then someplace else it'll grab it?
Yep,
Okay. And those are versioned?
those are versioned.
Is that in the YML file?
Yep.
Described, all that information is effectively described there.
Exactly. And you just basically, because we're going to have a set of APIs that we define in the operating system itself, but then users can use this for their build systems additionally to satisfy those dependencies.
Sounds like it.
Well,
That's what
it's just a build system rule for you.
in terms of a C interface,
Yep.
and I say I'm supporting the console interface, is it just that I implemented this header file, or is there a more formal schema on top of that?
It's just a header file.
Okay, so how do I assert that I've actually implemented that interface?
You provide the header file and say that you implemented it, and we believe you. I mean,
Sounds like.
yeah, I mean, the goal here, really why we use the APIs, is for those cases where you don't want to have a specific dependency in the package. So you don't want to depend on a specific package, but you want to depend on an API being there. And then you want the build that to come from another place. Because for us, if you look at if you look here at newt, we manage targets for a device, right? So depending on what you want to build, there's two routes to the target. There's the application and the board support package, and those two are combined to create an ELF file or an image. And the idea there is that you can write an app portably, and you can switch the board support package underneath it. Those are also the two roots of the build tree, right? So the application itself has a different route than the board support specific functionality. And so you may want to, in the applications build root tree, or in the libraries or the packages subsequent to that, you may not want to include a dependency. You may want that to come through the hardware support tree. And so the idea of the APIs is to kind of mitigate between those two. And I have title there, that's wonderful. So the goal is to make the system composable. What you want to be able to do is create a new project. When you go into that project, what we have is a package.yml file that defines the dependencies of that project. So if you look into newt as an example, we have a project.yaml file that defines for your blob project, here are your two dependencies. You have Apache Mynewt core, which is the core operating system repo. The goal was kind of early on to make this very, very slim. But what we actually found was when we're distributing an operating system, people want the functionality as well. So it's a fairly encompassing operating system. But then also here you have a second repository, which is Mynewt Arduino 0. And the reason we break out that repository from our core is that Atmel's header files don't match our licensing restrictions. But the goal of this project.yaml file is also to allow people to maintain their own private code bases as well. So what we typically see happen is somebody creates a new project. The default reference is Apache Mynewt core, and they install that. But they'll also have their own platform code base that applies across all of their products. And then they'll have individual projects for each of the products that they're actually developing. And so what Newt does is it goes and it allows you to install those dependencies. So the internet's not great here, so I won't do this. But if you look at repos, you can see the full tree of those packages in there, as well as project.state, which resolves it goes and it resolves the version 0-latest into a very specific version. So in this case, it's 0.9. And it locks the repository to that version. Newt then allows you to install and upgrade. So if you do newt install, it will go and tell you that they're both already at the right versions. If you do newt upgrade, it goes out and checks that you have the right versions. If we wanted to create a new project, and it would actually go and it downloads the dependencies for that project, which is going to take quite a while. And then it locks the repository to that version. So you can install and you can maintain these various versions. And so one of the kind of big decisions we made here was that in an embedded project, you probably don't want to have small little packages, but instead you want to have fairly beefy packages that you actually go and install, right? So the kernel itself is a ton of source code. You probably want to go and manage that. And so that's why we broke out the concept of projects and repositories and packages. So packages are individual build system elements that you can include in your build tree and build things with. A project is a collection of packages, and then a repository is a versioned collection of packages. So what we've done is essentially the remote repositories, in the master branch, they have a definition file that points to a Git branch. So when you have 0.90, that points to a Git branch, which is branch 0_090. You then have a version tracking tag, which is 0-latest, and 0-latest points to a specific version, right? So in 0.90, if we want to update that to 0.10, we update that to 0.10. And the idea there is we then tie that into our versioning scheme. So our versioning scheme says that if a minor version is upgraded, it'll only be bug fixes. If a revision is updated, it's only bug fixes. If a minor version is updated, it's only new features. And if you change the major version, we can do whatever we want. And so that's kind of the contract we have with our users. And so then people can actually stay on tracking branches. So they can say, I want to be on 1.0-latest. And they know they're only getting bug fixes between those versions. We then resolve those and provide upgrade functionality for these repositories that they track against. I don't know if that makes sense. Yeah. So build, in the build system, there's a couple of different things to look at. Obviously, one of the major things that we do is we bundle tool chains. So we expect certain versions of GCC to be there. Most of our code is written to GCC, but we also expect certain programs like OpenOCD or JLink. We have those versions all compiled into a Docker image so that people who want to go and download and install our source can just get the Docker image of Newt, which has all of the build and debug toolchain and all of that supported for them. And the goal there really is so that people don't have to worry about their compiler versions. We worry about their compiler versions for them. We worry about the debugger versions. We bundle all of that and distribute all of that as a part of Newt so that when you download Newt, you don't have to worry about any of that stuff. That does make, obviously, having multiple compilers kind of an issue. We kind of made the decision very early on that it was GCC or bust. We'll probably go to LLVM as well, but traditionally in this space, you've seen IIR or ARMCC. There are benefits to those compilers, but just we thought the benefit in general of just having everybody use the same set of open free compilers was probably a better trade-off for us.
Have you considered cases where you need 2 compilers for a specific target device?
Other cases?
Yes. So there's, for instance, on the AMD platform, you've got a separate compiler for the GPU that is LLVM based, but you also have the primary CPU, which is GCC. So, and there's other cases like that.
So we don't include those compilers, but what we do is we have compilers are a package as well. So the compiler definition is compiler / ARM none EABI GCC for Cortex M4. And there's a package specifically for Cortex M4 that we bundle. The board support package lists that compiler as a dependency, and then the build system is aware of a package type that is compiler. And so the board support package is really what defines what compiler is used for the rest of the system. And that actually, so the hierarchy that we've done is, so what we've done is a little bit, I think, different than other people. We just think that the BSP is going to define most of these things. So for example, for our driver interfaces or for our HAL, any of the initialization elements that we use there are chip vendor specific structures and header files that we allow people to provide into init when they create devices or a device tree or any of that stuff. What they do is they register with the operating system and they say, oh, all right, I want to initialize device ADC0. Here's the chip vendor specific header files or structures for ADC0, and call me back at the kernel set level of initialization, or call me back as the primary level of initialization. And then those header files are passed opaquely to init in the kernel process. So the board support package really defines all of that, and it defines things like compilers and everything else. So this is not anywhere else in the Makefile system except in the board support package. So if you wanted to do 2 different types of compilers, you'd need 2 different board support packages that you need to compile for, but you could use different compilers under there. So for M0, M4 cases as well.
Your own setup system, which is very similar to that. Did you see any disadvantages of not doing that?
We did. We started with submodules. Mm-hmm. It was just a nightmare for us to maintain, and we were just not very good at it.
So was there some downsides to it, or just like some specifics, like there is something wrong with it that you fixed in what you did?
Yeah, I mean, I think if we had known how to do it properly, we probably would have. It probably would have been okay. So what we do is we just essentially, when we download and install a remote repository, we git clone it, and then we check out the branch in that git clone, and just leave it like that. There's no submodule definition that we have within the repository itself that then automatically downloads or manages it as a submodule. What you can do is the project state file locks to a specific version. So you have the project.yaml file that says, I want 0 latest, right? That then gets resolved to 0.90. That gets placed in a project state file. And you can resynchronize your project from the project state file so you can have a consistent set of interfaces. So if you don't want to check in those repositories, which is kind of why you would use a git submodule, you don't have to check in those repositories. You can just recreate the exact setup from a project state file. But we were just, it was a nightmare for us to use submodules.
Yeah, I guess Git submodules can do the same things as well. So the second question is, when you consider external projects, can you also, does it have to interface with your build system, or they can be any independent module?
We're still working on that. We've taken some steps to make that a little bit easier. So the major one being chip vendor SDKs that we want to actually go and include. So what we've done there.
I guess I'm curious from people, because I think this is a little different view than I was thinking about coming from a Linux perspective into the microcontroller space around composability of software. And so I think, one of the things I've seen from working on the Zephyr project is I'm more concerned about how we deal with external packages, pieces of software, mbed TLS, external SDKs, TinyCrypt. There's just all these packages, the protocol stacks, right, that are separate packages, kind of are developments and so forth. And, there's obviously a difference. So I think that's the class of problem I was having in my mind. And I think there's a different class of problem that you guys are coming from, which is, I think, as valid about packages of software, somewhat internally built, but also towards how kind of you've taken the OS view that Mynewt's taking as well, about the separation and distinction of breaking things up, where I think Zephyr takes an approach of that's more everything's together, file system, IP stack, console, all that kind of stuff. And so I'm kind of curious as far as from a application point of view, do people see this value, need, problem? Is it an issue, just from because it's not one I've been even thinking about, is to kind of, drawing the line at the sand of kind of what the OS provides and maybe a BSP SDK, however you want to think about it, and then leaving how an application system product is managed to themselves, so to speak.
So I think in Zephyr, we are actually doing what Mynewt does in a completely different way. So we are doing that. So, you look at SOCs and BSPs and boards. These are basically modules because you can actually interchange them. When you look at TinyCrypt and mbed TLS, exactly the same thing. By providing one single API actually to talk to the crypto. The way we do it is probably different. Looking, for example, at Mynewt, and different file systems, where do you implement the API? Is it part of the OS or is it part of the module itself? So who does provide the .h file?
So we have fs/fs, which is the file system API, and then we have fs/nffs, which is our log structured flash file system. And so NFFS provides an implementation of the file system API.
Okay. And this would be actually exactly the same APIs, basically.
Yeah.
Different implementation, and they would be part of the package.
Yep.
And not part of the OS. So I have actually, so basically, it's not like I have an API which is part of the OS with different implementations that implement this API. But no, there comes a package with everything in it, including the API itself, that I add to my application in this case.
Well, that's right. So what essentially happens is you have Apache Mynewt core /fs/fs. And if you're an application that's using a file system, you're going to include that as a dependency. And that contains a set of functions that point into the various file systems that then register into the system. fs/nffs is an example of one of those file system implementations. There are others like fs/fat, which we're adding support for because of whatever. So there's a defined interface in the fs/fs package, which defines a set of handlers for seek, open, close, all of those things. And then the individual file system packages themselves register in, and the board support package then creates the file systems that are on the system. So the board, right, you're writing an app, and you say, I want to open a file at /x/y. You include the FS package to do that, and you open the file at that location. You expect it to be there, or you can use standard kind of Unixy file system functions to discover the file system. And then the board support package actually is what defines which file systems are included and where they're mounted.
So going back, sorry, go ahead, yeah.
So I'm still learning this, but it seems to me as though you've defined at a very high level the general components that you want in your OS, along with a set of interfaces that can then be replaced by any particular implementation. And to some extent, this is kind of the Wild West in terms of, you can put whatever implementation you want in there, and that's driven by the BSP. To Kumar's point, that's a different focus than generally what you see. I'm not as familiar with Zephyr, but obviously in Yocto Project or Open Embedded, there's more of a monolithic idea of everything's going to kind of come together, which goes to my question about the tool chains. Everything is going to kind of play together into a single build that you're going to end up with a final image with. So it seems like this is more, as you said, composable, but by design, you really want everything to be replaceable with something that the vendor wants to do, or the application developer wants to do. Does that sound right?
Well, I mean, it's more how we lay out our system. So in the case of file systems, right, we think that there should be an abstract API in the operating system in a Mynewt core that goes across multiple file systems. So we have a file system API. That's not enforced by the build system in any way, but the build system allows us to go do that. In other cases, we just directly have implementations of things. So like our Bluetooth stack is just a direct implementation of the Bluetooth host and a direct implementation of the Bluetooth controller. The only case where we make things pluggable in that stack is at the driver level, right? So we have driver implementations for NR51, 52, and native.
This is where So I think, and kind of so Zephyr is kind of, I think, sort of like Linux in this respect, and from an OS, how we think of an OS, and it kind of differs, I think, in the microcontroller space about the executive, which is a very extremely small, just, piece of kind of what we would think of like kernel core would be, but in Zephyr, much like Linux, where we have the drivers directory, file system, networking, right? All of that is revisioned under one Git repo. We use kconfig to do selection, right? So a lot of that stuff is being, the equivalency is through the system here with the YML files and dependencies, and if we were to version everything independently and break it apart, and so to speak, as part of what is going on kind of what, where one draws the OS line and thinks about it is kind of one aspect. And then I think that was kind of where I was starting to ask the question of, there's also the ability to deal with this for application code, and then there's the third party, which was the viewpoint I was coming from, kind of piece where we come in from like OE or so forth, where you're building, the kernel's a package, but then you've got, just all of your user space stuff that we're building. Now, obviously, there's not this user kernels, or not this user space split typically in these environments, but there is that kind of, protocol stack, so CoAP or an HTTP library or mbed TLS, or there's all these other things that are application packages or pieces of software that I'm curious, and obviously it sounds like you guys are starting down that path with obviously some of the SoC SDKs, but I'm kind of curious what else on that side.
Yeah, so I mean, I think, we are very similar to Zephyr in the way that, Apache Mynewt core, which is that repository, does contain a version set of packages, right? And we distribute file systems with that and Bluetooth networking stacks and all of those things in Apache Mynewt core. The package dependencies is more of a build system thing that allows you to, we make it very configurable, mainly so that people can reduce code size, because you don't want to bring a whole bunch of stuff into the build system, and so that you have a very clear picture of what's getting built and a lot of control over what gets built in the system so that we can keep code size down. The second point you were making, I think, is a good one. I think scripting languages are a perfect place to kind of look at how you might do that, right? So I don't think, we bundled ELU into the core, and I think that was a mistake that we made.
They bundled
Lua into the core. I don't think the operating system should contain a scripting language. That's my opinion. It's.
I agree with you.
Yeah.
I don't think many people are going to
Yeah.
disagree,
But script, but yeah, kind of composing that. So now you want to have Apache Mynewt core, and if you look at most of the scripting languages out there, JerryScript I think is probably a outlier. They actually contain their own operating systems in them, right? So the scripting JerryScript, the ones people use in this space are Esprino and MicroPython. You go through, they have their own house, they have their own board support infrastructure. They've basically built an operating system, bare metal operating systems, and it doesn't, to me, make sense that all of these different scripting engines are going to have their own operating systems. Eventually, they'll adopt like Zephyr or Mynewt or something else. So where you would use the composable aspect of this is you would want to have those scripting engines to have a dependency on Apache Mynewt core as a repository, and you could specify that in a project.yaml file. And they would want to depend on a specific version of Apache Mynewt core, and that would be a source code dependency, right? Along with a set of APIs that were exported and a version along with that. So what you would do, in that case, is if you looked here, you'd have a project.yaml file, and you would, in the project you've created, so you create your own custom project as a user, right? And you say newt new, my project. You would then, in that project YAML file, say, I want to have Apache Mynewt core, and I want to have this remote repository, which is JerryScript hooked into Apache Mynewt core. This would install both of those, and then you could go and create a compilation target to go build that system. But I think you want those, initially what we did for the package management system is we had all these little packages. So libsOS was a separately installable package, or pretty much every package in our system was separately installable, and it just became a nightmare to maintain, as you might imagine. And we actually tied in the concept of building and package installation, which are completely separate. So what we came to is you want to be able to redistribute kind of big chunks of source, and you want to allow people to manage big chunks of source. But then once you go within those chunks, you want to have a lot of flexibility and configurability so that you don't build the entire world, right? And a lot of what I don't like about the Linux side of the build systems was the fact that pretty much everything gets built, and then it's left to the linker to sort out a lot of this stuff. And so you're constantly like going through and saying what's compiled in, what isn't compiled in, how do I know what's going on here? And so a lot of the dependencies is also just to be very clear about what's getting built, how it's getting built, and letting users write that out.
So I think you need like same SDK across the whole ecosystem to support something like that. Otherwise, what's the versioning control and all those issues that will come along, right?
Oh yeah. Well, you don't need the same SDK. I mean, you just need it all to be in your world, right? Kind of there is a tax for participating in this world.
Yeah.
And you have to kind of take that tax. Otherwise, it becomes hard to manage. But there are benefits to it, right? Like namespacing things. I think every chip vendor header file that I've ever seen that's ever gotten delivered has a completely different namespace in it. And that's really, really painful, right? We've added some build rules to handle that. So what we do for package types that are SDKs, for chip vendor SDKs, what we essentially do is we go in the directory and we recursively compile every element of the SDK directory. We also recursively add into the include path all of those header files in order to build those, and then have a set of rules that allow you to define what you compile.
I was curious, and Sam, if you don't mind, just kind of from an embed point of view, or if you can talk maybe a little bit, just similarities, differences from what you've heard about composability, dependencies, and where embed is today, maybe, other things, so forth.
Okay, so anybody who saw the presentation Monday, mbed, the current 5 version we're working on, ships without yotta, without this type of a detailed system included inside of it. And this conversation brings back a lot of things that we'd gone through over the last 12 to 18 months, and it all just resonates, right? module fatigue, module fragmentation is a very, very hard thing to do. You know, are you compiling the OS, or I'm sorry, are you composing the OS, or are you composing applications? These are very clear things that, being honest, we got completely wrong the first time around, which made the adoption of our software very hard. At the end of the day, I think the most important thing to remember is it's not about the automation and what we're doing inside of here. The tools are important for that, such that we deliver good software, but it's also about how these fit into the environments of people who are going to adopt the code and go build products with it. And you know, part two, what we got very wrong was the fact that a lot of the dynamic installation or injecting scripting with kind of C-style development with the IDEs and tools that exist that are commercially available and that big product companies who are shipping millions and millions of devices are using. Those two things are actually kind of opposing. And when you go talk to those companies about their engineering practices and the requirements that they put on their teams to deliver quality products that they can measure against ISO standards and other things, this world doesn't fit. It's really cool for I don't know, entry level, and I think maybe in a couple of years, it's going to be something again that does fit. SimSys is going down a path trying it with the packs, not as in your face, it's everything's there and you kind of clicky choosy pull it in. And so where mbed is now at this point is much more of where we were 3 years ago, which was, yes, we believe repositories are important, not so much the type of the repository, so whether it's Git or SVN or Mercurial, it doesn't matter. And one of the pain points had been we were very tied to Mercurial before, and so then the branching model of Mercurial and the branching model of Git is very different with respect to how heads and masters and remotes work. So I don't know, current position is, at least for mbed 5, is a major series of development that if the software's there, it just builds, and we should all work out, the namespacing issues, the unique file names for, because you build these build systems and you work around these things. They're very flexible. You can have multiple .o files, and it links because you're passing the path to the linkers. You go to an IAR or even an MDK environment, and that fails. Well, the moment that somebody is taking your code in who must use one of those tools in their environment, they're now modifying your code, whether it's in tree or out of tree. In my opinion, we just failed. So those are all things very important, and I think just generally good design practices for these OSs is what's being delivered. The packaging stuff's great, and whether it's branch models, whether it's zip packages in other repositories, we'll get there. But right now, our current position is pretty much, if it's in a repo, it comes in and we build it, and it has a lot of limitations. But given those positions, it moves us forward to the point where we can continue to kind of study and try to solve these problems.
Do you guys try to address at all, and I'm trying to figure out how terminology for us all to talk consistently, because I think that's definitely something kind of coming out of this session I know we'll have more conversations about, but kind of the layers above. So I'm trying to think of a good example. So a CoAP stack, maybe that's not something you guys, it's not, and maybe that's not the best one, but just something like that, that is kind of an application potential thing. Maybe it's some third party, someone's developed the CoAP stack that's out there. Maybe there's still some integration that needs to be done for it to work on mbed. Is that something you guys deal with yet, or is that something you kind of let that sort of push to the application developer to kind of manage themselves?
So the object-oriented approach to development has helped us with that a little bit, meaning we follow trends. We watch what people do. We watch what's hot. We obviously have our own interests as far as what we think should be inside of an OS, and things like WebSockets and CoAP and such. There should be one. There's not, if it's written well and if it's written against the standard, there shouldn't necessarily be a need to bring in different pieces like that in some cases.
Okay, so maybe that's not a good example, but let's say for some reason there's a file system that for this customer, there's an open source project. It's not one that you guys have seen really a vested interest in, so it's not part of mbed standard. what is the story, is it,
Right.
yeah, what's the story kind
So,
of?
yeah, so what I was getting at with that is the story is for common components, there is that object-oriented contract to the developers, which we say in many cases, sometimes it's in the OS and sometimes it's just a piece of code that we float out there, which is here's an interface and we think this is quite good. And there's a contract for people developing on the top, and then there's a contract on the bottom for people porting against it. And as those things mature and as we find out how people use things and what the requirements are, sometimes those APIs come into the code base such that, one could be enabled as a feature or excluded and replaced by, again, an external piece of software, whether that's the file system that then provided the lower level contract. If the OS had the API is still exposed, and if it's still kind of under development, maybe alpha or beta as to what it does, and it's typically just floating around out as a repository elsewhere that these pieces can bring in and distribute themselves. And it's really about learning, what and how people use these different things.
I think we have a couple of minutes left, so I just maybe open up, anyone generally have any questions or?
Yeah, one of the distinctions is that I was talking to Simon Ford about, the iterations through mbed, and do you talk about tooling for consumers or producers? And I think, much of the MCU space is consumer focused, where they want a single ID and a single tool chain, and it, just point and click and build. Whereas many of the people in the room, I think, are more producers, and they're used to command line tooling and multiple ISAs, the multiple tool chains, and have to deal with that. And so do you differentiate between a tool set for producers versus tool sets for consumers? And so we tried to do packaging and build from TI and miserably failed. So I appreciate the challenges, and we have similar concepts and challenges, but we've moved more towards a internal tooling thing that generates external artifacts that makes it easy to work in IAR or GCC or that sort of thing. And anyway, I just throw that out as a distinction. But and to your point, I think being able to compose a single executable, which is different than the Linux case, is really a challenge here. So if we're going to be able to bring in third-party algorithms and so forth, it would sure be nice if you could build them the same way as when you link or build with your OS. And so I appreciate the goal. I'm not sure how to solve it, but I think it's something we'd like to.
That's a perfect point. Because there is a different challenge from an ARM or a TI perspective than it would be from our perspective, right? We don't, personally as runtime, don't care about people who use IAR, right? And there's a lot of people who do use IAR, and as TI, you really have to care about the people who use IAR, right? Because they're probably 50% of your business or something. I mean, it's a very, very popular tool chain. It's very, very popular in industrial applications. Whereas for us, it's a little bit less of a deal. And so I think what we would want from chip vendors and from providers is if we could all agree on a directory structure, and it doesn't have to be our directory structure, that these things get delivered in, or there was a standard set of ways of delivering packages, it'd make it a lot easier for systems like ours to then integrate those. Because today what we do is a lot of basically regex rules that we include into our build system.
Sorry about this, because I just walked into the next session on security. I don't want to delay it, but is it possible to summarize what you have decided to do around it?
I think that's best taken offline, just because I don't think it's going to get done.
Okay.
We're already running late.
That's all right. And I'll throw a bit of opinion in. Code that codes have been compiled in many different ways is horrible to look at. Use GCC and everybody else's tool chain should work like GCC, and try and separate out the kernel from the application, which is hard in a single root image. That's my opinion. Won't kill any conversation.
No, and certainly that's our opinion as well. I think that is somewhat.
Otherwise you'd go down this path of madness.
And at the end of the day, it's the result of the system is really to make it compile. Like the user wants to get your operating system, and they want to be able to compile it and load it on a board with the flash laid out, with all of the drivers set up. And so build and package management, if you make some trade-offs that are not going to be nice for everybody, it's going to make it nice for the user who downloads it.
I get the point between the difference between someone who wants to port this to a new chip and add a device driver and I just want to take and build my thing.
Yep.
And I think that's a good distinction.
Can we cut it there?
Yeah.
Thank you, Sterling, everybody. I know we're running short on time, but maybe,
2 minutes?
yeah, a couple minutes for also, then needs a quick bathroom break.
Yep. We'll start again in about 2 minutes.